Hello, everyone. We're moving on in Statistical Methods for Rates and Proportions, Chapter 3, Assessing Significance in a Fourfold Table. We're still in Section 3.2, Exact Analysis of a Fourfold Table. This is Part 2. So at the end of Section 3.2, it starts to talk about what happens when our cell size is low. In other words, inside the table, we have some values, even just one value that's less than 5. So we're going to create a scenario where we have a table with small cell values. Remember, we can set up our ni dot, that's our row sums using the apply function. We can get our n dot j's, which are our column sums, again, using the apply function. And we can get our n dot dot, which is our overall table, by summing up our entire table. All right, a new function that we're going to use in R is called factorial. That's just the regular factorial. 3 factorial would be 3 times 2 times 1, or 6. I just wanted to show you a quick example so you know that that's what it's doing. And then following equation 3.9, we can use the hypergeometric distribution. And from our table that we've created, we have all of the ni dots as well as the n dot j's that we need. So we can get p observed as the probability of observing this table is 0.1190. And that's given the fixed marginals. So if we assume that we can't change any of the row totals or column totals or the overall total, what's the probability of observing this particular table? All right, that's a lot of individual work. And so what I wanted to do is just create a function of my own that would output this p dot observed. So I can define get.prob, which I made up that name, as a function. And the function has inputs, and I can define whichever inputs I would like. And then I'm going to have this curly bracket at the beginning and this curly bracket at the end. So I'm giving it inputs as each of the individual cells of a 2x2 table. So N11, N12, N21, and N22. And what I did is I took my code from above, right? And I just created an entire function that did all of that code. And then the very last thing is what the function's outputting. So I said, output this probability for me. So I'm going to run that function. And now the get.prob function is available to me whenever I choose it. So here, I'm doing the same thing as before. And I'm just saying, tell me the probability if I have a table that looks like a 2, 3, 4, 0 table. And just to double check, I get the same exact probability as I did before, 0.1190. So I'm pretty confident that I wrote my function correctly. And what we're going to do is say, if I have these fixed marginals of 5, 4, 6, 3, what other tables might I observe? So if you notice, we could have 3, 2, that adds up to 5, 3, 1, that adds up to 4. 3 plus 3 adds up to 6, and 2 plus 1 adds up to 3. So this table is a possible table given the marginals that we observed. That has a probability of 0.4762. 4122. The row marginals would still be 5, 4, and the column marginals would still be 6, 3. And I can get the probability of observing that table, 0.3571. Now, 5013 is the only table left. That's a row marginal of 5, and then a row marginal of 4, and then the column marginals are 6 and 3. If I get that probability, I get 0.0476. Now, our original table had a probability of 0.1190. And if you do a quick spot check, those all add up to 100%. So we can say that our p-value is the probability of being as extreme or more extreme than the one in our sample, right? Given the null hypothesis is true. So given that we have fixed marginals, what is the p-value of our table? As extreme or more extreme. So it's the probability of the table we observed plus the probability of a more extreme table. So we get our overall p-value is 0.1667. All right, well, just like usual, there's probably a built-in function to do this. And I'm going to use the Fischer.test function. And this will give me the Fisher exact test. So if I do Fischer.test of our table, I get the same exact p-value, 0.1667. So I'm pretty confident that either way, I get the right thing. Now, if I want to know more about this Fischer.test, I can actually just type the name of the function, and it should output what the function's actually doing. And this looks quite complicated, but what it does is it does all the pieces that are needing to be done. And if you're interested in learning more about how they built it, then you can actually go through and look at the code and see if it makes sense, what it's doing. This isn't required, but anytime that there's a function, you should be able to read the code because this is an open source program, which is very nice. And you can learn a lot from that. I can even input my function get.prob, which if you notice, my function is not as complicated as theirs. But theirs is making sure that everything's been, it's checking all assumptions and doing a lot of different things, where my function is just for the use of my particular case. So I didn't have to do something as complicated because it's only for my use. But I hope you learned something today about the Fisher exact test. Coming up with how the tables look for a fixed marginal frequencies. It's not completely difficult, but it just takes a lot of effort to make sure you've gotten all the possible tables, whereas the built-in function just does it for you automatically. So I hope you guys have a great day, and I'll see you on the next video.